So the next workbook assignment, workbook number 6, is due Monday at 11:59 p.m. So I'm going to dedicate the Monday class session to talking about those problems. So although you can work on them before class and check your answers with me to see how I do them and see where you might have went wrong, I am talking about them regardless, so you can do with that as you please. Besides for that, tonight there is the homework on graphs of rational functions that is due. And this is a pretty, it's a pretty tumultuous section. Some of these problems have 12 parts to them. I know it's not the most ideal, but what I figured I would do, so for my other section, I covered 2 of the problems in there, and some of these problems take a while to cover. So I figured I would just post the links to those problems that I did for that section. So those are already posted in your lecture links, and I'll just talk about 2 other problems from the homework that is not from that video nor from my lecture video. Just so you have more variety of problems I have worked out, just in case you want to see them. So with that being said, I'll go ahead and find a problem that I have not talked about yet. So number 4, I've talked about in it's example 1 from my lecture video, so I'll skip over that one. Number 5, I talked about in the lecture I gave for my other section. And as I mentioned, I already posted that right here. So you can already go ahead and watch that. So I did that problem in this review session, so you can check that one if you would like to. So I do not believe I've talked about this one in either my lecture or the last review session, so let me make sure. Okay, so I'll go ahead and talk about that one. So this one is number 6. Okay, number 6. Unless anyone had any problems that you recommend that I work out, or you definitely want me to if you've worked on this homework already, I'm happy to work out any specific problems you might have. If not, just let me know after this problem and we can work on that one next, if you have a specific one you want me to do. Okay. All right, so they give us 5 divided by x squared minus 16. And so they want us to do a bunch of things to slowly construct the graph of this rational function. And so the first thing they want us to do is factor this rational function. And so when they say factor a rational function, remember, a rational function is a polynomial divided by a polynomial, and we can factor polynomials. So factoring a rational function means factoring the corresponding polynomial functions. And so that means, so you might notice that x squared minus 16 in the denominator, so of course the numerator, it's just the number 5, so there's nothing to factor. The denominator is a difference of 2 squares. That is a difference of 2 squares. And the way we can factor that, hopefully you know by now, is x plus 4 x minus 4. And the reason why I choose 4 is because that is the square root of 16. So that is the factored form here. We factored out the denominator. And if the numerator could have been factored, we would have attempted to factor it as such. We can move on by determining the domain of the function. And so to determine the domain of a rational function, it means setting the denominator not equal to 0. So we set the denominator, not the numerator. The numerator is just left out completely. We set the denominator not equal to 0. And we solve for x. But since what we set equal to 0 is already factored, then that is equivalent to determining the corresponding zeros of the factors. So we've done this before. Factored forms are good because we can pick out the zeros really easily. It's just the opposites. So we would conclude that x cannot equal, because this is a domain, so not equal to -4 or 4. So I'm going to put it in this blank because for answer choice C, it has a not equal sign as opposed to a less than or a greater than or equal to sign. It also goes on to ask what the function in lowest terms is. That's a fancy way of saying that if there is a factor in the denominator and the numerator that are the same, go ahead and cancel those out and then give us the simplified form. We do not have that in this problem. There's no common factors for us to cancel out. So this is already in lowest terms. Now we're going to go ahead and look for the x-intercepts and the y-intercepts as well. So move on to intercepts. So we'll start off with the x-intercepts, which means set y equal to 0. So we are setting the whole function equal to 0. I'm going to use the simplified form that we have, this factored form right here. But we are setting the whole function equal to 0, and we're trying to solve for x. So we can go ahead and cross multiply, or additionally, or in other words, multiply both sides by the least common denominator of x plus 4 times x minus 4. And what we get is 0 times that denominator term is equal to really 5 times 1, or just 5. But luckily for us, 0 times anything is 0. And then we hit 0 is equal to 5, which doesn't really make any sense. And since we hit this illogical conclusion, then what we can conclude with is that there are no x-intercepts. That's it. So there's no x-intercepts in this problem. So if anything, we're leaning towards answer choice B. Because notice it says no x-intercepts, as the other parts have a space for x-intercepts. So we'll think about B for now, but we still have to find the y-intercept, if there is one. Which means we set all the x's equal to 0. So the function is 5 divided by now 0 plus 4 times 0 minus 4, because now we are setting all of the x's equal to 0. So this is 5 divided by negative 16. Because in the denominator, you end up getting 4 times negative 4, which is negative 16. And so that's it. That's the y-intercept. They want the y-intercept as a simplified fraction. So we will pick or express the y-intercept as negative 5 over 16. So I choose answer choice B because it has a y-intercept blank and it excludes the existence of an x-intercept. So this next part, thankfully, we don't really have to do this next part because it says determine the behavior at any x-intercepts. But guess what? We don't have any x-intercepts. Over here, we said there are no x-intercepts. So we can say there are no x-intercepts and we can move on. Now we need to determine the vertical asymptotes. So the vertical asymptotes, as I mentioned in my workbook session from Monday, the vertical asymptotes are normally always the domain, just with a slight variation. Most of the time, the vertical asymptotes requires us to take the domain, which we found up here, but just put an equal sign instead. So notice I swapped out the not equal sign with an equal sign. And the way that translates, so we have two vertical asymptotes, which is why I'm going to choose answer choice B, because it does say two vertical asymptotes. But it wants it as the leftmost and then the rightmost, which means it wants the smallest one first and then the largest one. I'm going to write these as separate equations as well, because it does say type equations, which means you better have an equal sign somewhere. And so I wrote down the leftmost one and the rightmost one. And now, so something we will have to address is determining the behavior on either side of the asymptotes. So this is the behavior around asymptotes. So generally what we have to do here so what I like to do is think about for each vertical asymptote, we're going to pick two values because they want to know the behavior on the left side of the asymptote and the right side of the asymptote. So for the left and for the right, we're going to choose two slightly different values for x. For the left, I'm going to choose negative 4.1. It's really close to 4, or negative 4, but it's not quite 4. And negative 4.1 is to the left of negative 4. For the right, I'm going to choose negative 3.9. And what we're going to do for both of these is we're going to plug them in and simply see what kind of number do we get. Because with asymptotes, what happens is at any particular asymptote, generally the graph will either trace it going upwards towards positive infinity, or we'll trace it going downwards towards negative infinity. And the graph is asking, well, which direction is it going in? Now, luckily, we only have to look at one of these, either left or right. This is provided we have a good sense of determining the multiplicity. So really, we're only going to look at left. Because with the right, we're going to use multiplicity to figure out the right side without having to do the extra work. So the left, we're going to plug in negative 4.1 into every x value. So remember, the function that we started off with is x plus 4, x minus 4. But now we're plugging in negative 4.1 plus 4, negative 4.1 minus 4. And let's see what kind of number we get from this. So I'm going to plug in the denominator individually. I'll bring everything together, and I see that I get a positive number, which means on the left side, so that's how you would, this is how you would interpret this. On the left side, we get a positive number. So that means this will be approaching positive infinity. So that means the graph on the left side will be doing something like this. That's what we've just determined. Now on the right, we need to know the multiplicity of the asymptote. So asymptotes have multiplicity. And remember, multiplicity, it's a fancy word that means the exponent of the factor. Remember, this was the expression that we had. The exponents for both of these are ones, which tells us that their multiplicities are 1 for both asymptotes. And remember, what an odd multiplicity, so 1 is an odd number, an odd multiplicity tells you that in the previous section that you would cross at that value. But at an asymptote, the idea of crossing is a little weird because we normally don't cross or interact with asymptotes really. So the generalization here is that the infinities will alternate. So since the multiplicity is 1, it means crossing. So since multiplicity of x is equal to negative 4 is 1, which is odd, the direction will alternate or cross. So we found positive infinity on the left side. So on the right side, that will alternate. So that means at that asymptote, the infinities will cross. You will end up getting the same thing for, and this was all for one of the asymptotes, because we found two asymptotes. This was all for the asymptote corresponding to x is equal to -4. So let's go ahead and figure it out for the other one. +4 was another asymptote. And for the left, we're going to pick a number that's close to 4 on the left. So I'm going to pick 3.9. Just a number that's close to 4 and it's on the left of 4. So from here, I'm going to go ahead and plug in 3.9. And we can already tell that this is going to be a negative number. So this is negative infinity. And since the multiplicity of 4, we saw, so same argument as before. And the right side will be the alternative, positive infinity. So both of these alternate. That's why I'm choosing answer choice C here. It approaches infinity on one side and negative infinity on the other for both of these asymptotes, because their multiplicities are both odd numbers. They're both 1. This is a thought process that once you're familiar with will save you a lot of computation. We can go on to find the horizontal asymptote. It's the horizontal asymptote. And remember, this is found by comparing the degrees of the numerator and the denominator. Degree of the numerator is 0 because there's no x, and the degree of the denominator is 2. Now you could have found this out from this version or the factored form that I was using afterwards. I suppose to keep things consistent. The degree is still 2 because there's 2 x values there. Or you can additionally figure out the degree by using term domination. But using this, when the degree of the denominator is larger, it means that the horizontal asymptote is y is equal to 0 always. That is always what happens when the degree of the denominator is larger. Your horizontal asymptote will always be y is equal to 0. So that is the horizontal asymptote here. And we never have an oblique asymptote. So for every problem that you come across, you're not going to have an oblique asymptote, so you don't have to worry about that. So the problem goes on to ask, well, where does the graph intersect the horizontal asymptote? So graphs do intersect the horizontal asymptote. They can't intersect the vertical asymptotes, but they can, in some situations, intersect the horizontal asymptote. And the way we figured this out is by setting the function equal to the horizontal asymptote. So we said the horizontal asymptote was 0. So we would be setting the function equal to 0. But you may notice this looks very familiar. We've already done this computation. We did this computation when we were looking for the x-intercept. So what happened in that situation? We cross-multiplied, and we found that 0 was equal to 5, which doesn't make any sense. We hit an illogical next step. So there are no points of intersection with the horizontal asymptote. So this is no intersection. The horizontal asymptote. So there's no point at which the graph intersects the horizontal asymptote. So now what this second to last part says is, let's go ahead and what this second to last part says is go ahead and figure out what part of the graphs are above the x-axis and which parts are below the x-axis. It gives us a good idea as to where everything is at in relation to the real zeros, as they call it. So they want us to find the real zeros of both the numerator and the denominator. So the zeros of the numerator, there's none. There's no zeros for the numerator because there's no x. But for the denominator, the zeros, as we already found, -4 and +4. And so now they want us to use these zeros to, it goes on to say, choosing a number in each interval. So what it wants us to do is this kind of number line test where we plot the zeros that we found, and they want us to pick random points. So what we've done is we've taken the number line, we split it up into 3 sections. Split it up into this section over here, this section in the middle, and this section on the right. So with all this being said, they want us to use these test points to determine which parts of the graph are above the x-axis and which parts are below. Now, the fortunate thing for us is that we actually already found this answer, because we already know the behavior around the asymptotes. So let's go ahead and scroll up and see what we found. To the left, so we found to the left of -4, it's going to be positive. And to the right, it's going to be negative. So left of -4 is positive. left of -4 was positive, and the right is negative. And then for +4, we found that the left part is negative and the right part is positive. So the left part's negative, which we already have. The right part is positive. So what this tells us, why I'm only putting these signs, these symbols, is because now it tells us that this part of the graph and this part of the graph are both above the x-axis. And so in interval notation, that is -∞ to -4, and I'm using a comma to separate, and also 4 to infinity. So I'm taking the interval notation of these two intervals, and I wrote them down respectively. So I'm going to use the option for part A. Because this also has a blank for below the x-axis. As we can foreshadow, there is a section there. And so below the x-axis, that's where the negative sign comes in. That's what the negative represents, below the x-axis. And so that, in interval notation, it's -4 to +4. It's trapped in between those fours. Now, finally, we're going to take all of this information and use that to construct the graph. Now, if anything, we found 2 vertical asymptotes, which means that B, answer choice B, is definitely out. That only has 1 vertical asymptote. Same thing with part D. So both of those are out, and we're left with A and C. So now we have to choose between which one is which. But in the most recent step, we determined that the middle component has to be below the x-axis. Here, it says the middle component is above the x-axis, while this one says the middle component's below. So naturally, we choose C. Okay. So from here, you can go ahead and move on to another problem. And I think the one I want to do, so I did number 9 in my other class. So if you're interested in example 9, I did that one in the other lecture, which I did provide on my math lab. The one I want to do is number 10. This one is number 10. Okay, so the function x times x minus 1 squared divided by x plus 2 to the third So we start off by giving the function in factored form, which you may already notice, it is in factored form. Everything's factored already. So if anything, this is already in factored form. So that part's easy. Everything's already factored for us. Now we move on to find the domain. So A was factor. It's already factored. D is the domain, which means we set the denominator equal to 0. So the denominator is just x plus 2 to the third is equal to 0. But since the denominator is already factored, this means we just have to pick up the 0 from the factor itself, which is just -2. So really, we only get x is not equal to -2. Okay, so -2. Now it also goes on to ask us to find the expression in lowest terms. That means, as I mentioned in the last problem, this means if there's any cancellations, go ahead and apply those now, but there is no repetition in the numerator or denominator, so there's nothing to cancel. Everything's already in lowest terms. So now we're going to go ahead and find the intercepts of the graph. So the intercepts, there's 2 intercepts. Start off with the x-intercept, where we set y equal to 0. So that means we set the whole function equal to 0. So we can go ahead like we did before. Since this is a rational function, we can go ahead and cross multiply. Which fortunately for us, when 0 is multiplying that denominator, everything zeroes out. So really we just get 0 is equal to x times x minus 1 squared. And so now we have a factored form equal to 0, which means each factor will give us a solution. So actually we get 2 x-intercepts. So these are the 2 x-intercepts, 0 and 1. And out of answer choices A, B, C, and D, I'm going to choose A because I anticipate we will also have a y-intercept that we'll go ahead and fill in momentarily. So the y-intercept, we set x equal to 0. And really, we just get 0 because we're multiplying by 0 in the very front. So we just get 0. We just get 0. Okay. Move on to determine the behavior of the graph at any x-intercepts. We didn't have to worry about this in the last problem because there were not any x-intercepts, but now we have 2 of them. So we need to figure out the behaviors. We'll talk more about this idea of multiplicity. So here it's using the terminology of crossing or touching. So The first x-intercept we found, in fact, before I even write that, so this is, one more time. So we're on part E. This is behavior near x-intercepts. So the thought process for the behavior near the x-intercept of 0 at x is equal to 0, we need to determine the multiplicity. So which factor did 0 come from is the question. And 0, I'm going to write it on over here, as you'll see on the right side of my screen. 0 came from the singular x, just that solo x on the outside. So it comes right from this x right here. The multiplicity is, well, what's the exponent of that x? It's 1. Which is an odd number. So the graph crosses at x is equal to 0. So that should be your thought process, verbatim, right there. So we'll go ahead and fill these in later, because we have another x-intercept. We found that x is equal to 1, or that was another x-intercept, the value 1. And we need to figure out 1's multiplicity. So we ask ourselves, all right, where did 1 come from? 1 came from this factor right here. So what is the exponent of that factor? It's 2. It's the 2 right here. And 2 is an even number. So the graph touches at x is equal to 1. So we're going to go ahead and pick answer choice A. This answer choice A has an option for crossing and touching. So it crosses at x is equal to 0 and touches, but not crosses, at x is equal to 1. So that's it for that one. This is the immediate thought process you should have for this part. We go on to determine the vertical asymptotes. And again, the vertical asymptotes for the majority of the problems will always just be whatever the domain is, with the exception of the not equal sign being swapped with the equal sign. So in this problem, we said that the domain was x is not equal to -2. So all we do is simply say that now it's x is equal to 2. So there's only one vertical asymptote. So I'm going to pick answer choice C, which only allows one vertical asymptote. It does say type an equation, not just a number, but an equation, which means we need an equal sign. Oh, I forgot negative. I'm sorry. It should be negative. It's -2. So as you can see, I make mistakes all the time. It should be -2. So that's the one and only vertical asymptote. And from here, it wants us to determine which one of these options will fit for the one vertical asymptote that we found. Well, obviously it can't be A because it has two blanks to imply that there's more than one vertical asymptote. So it's got to be one of these two. And part B says on the left and the right side, do they both go to infinity or negative infinity? And then part C says that they alternate. One goes up and one goes down. Oops. So behavior near the vertical asymptotes. So we need to figure out what's happening to the left. So I'm going to choose a number that's fairly close to -2, but to the left of -2. So I'm going to pick -2, well, x is equal to that value. X is equal to -2.1. Because remember, with -2.1 would be to the left of -2. And we're going to plug this into every x. So now instead of x minus 1 squared over x plus 2 to the third, this is now -2.1 times -2.1 minus 1 squared divided by -2.1 plus 2 to the third. Let's go ahead and plug in all of that. In the numerator, I get -20.181. In the denominator, get -0.001. And when we put all of this in the calculator, I get a large positive value, which means positive infinity. It means positive infinity. And so to figure out the right, we need to figure out the multiplicity of -2. The multiplicity of x is equal to -2 is, so we need to figure out what the multiplicity of -2 is. -2 comes from right here. I wrote it on the right of the screen. So the multiplicity of that is 3, which is an odd number. So behavior alternates. That is, right is negative infinity. So positive infinity alternates to negative infinity. So that's why I'm going to pick answer choice C, which says that it approaches infinity on one side and negative infinity on the other, as in the infinities alternate. So that's at -2. move on to part G, which is determining the horizontal asymptotes. Well, really, there's generally always just one in this class. And this, again, has to, this comes down to the degree of the numerator and the denominator. So the degree of the numerator is 3. You can use term domination to see this, but you have 1x in the front and then the x squared as the next one. So 1 and 2, that just gives you the 3. And the denominator, same thing. There's x plus 2 to the third power, which just means that there's, when you use term domination, you would get x cubed. So what does that mean? Well, this means that the horizontal asymptote is the ratio of the leading coefficients. It's the ratio of the leading coefficients, which means whatever the leading numbers are, which in both situations seems to just be 1 and 1. So that means the horizontal asymptote is y is equal to 1. Normally we denote it as an equation, which makes more sense because it does say type an equation. So if you just tried to type 1, it's going to throw all this junk your way. So you have to put it as an equation. Y is equal to 1. And there's never an oblique asymptote, so don't worry about that one. So the horizontal asymptote is y is equal to 1. There's only 1. And there's never an oblique asymptote, so don't worry about that one. Now we're going to see where the graph may potentially intersect the horizontal asymptotes. I mean, most of the time it doesn't, but sometimes it does. So in this situation, it does not, and let's see why it does not. Most of the time it doesn't. Well, the reason why is we set the equation equal to the horizontal asymptote, which we found was 1. So we set the equation equal to 1. And when we cross multiply, we would get x plus 2 to the third is equal to x times x minus 1 squared. And so you would have to work both of these sides out, which for time constraints, I'm not going to do. But the good rule of thumb is that the majority of the time, there's not going to be a point of intersection, not in the scope of this class. And if it does come up, it'll probably be a really simple computation to solve. This computation is a little bit excessive. I wouldn't expect you to do that. So We'll move on to do the number line test as we did in the last problem. So this number line test requires us to find the zeros of the numerator and the denominator. And so since the numerator and the denominator are both already factored, and finding the zeros is really as simple as just picking out the zeros from each factor. 0 and 1 from the top, and then from the bottom, it's just -2. And then it wants us to construct a number line where we plot all of these. Now I'm going to plot them in order. So out of all three of the zeros that we found, I plotted them in order. So -2 is the smallest, then 0, then 1. And so we're going to go ahead and figure out which parts of the graph are above the x-axis and which parts are below the x-axis. And we're going to use multiplicities to help us with that. Now, it's very convenient that we already figured out the majority of this information in previous steps. We already had to figure out the behavior around the asymptote of -2. Let's scroll up and find that. At the vertical asymptote of -2, on the left side, it went to positive infinity, which is above the x-axis. And then on the right side, negative infinity. So to the left of -2, positive infinity. To the right, negative. So if anything, we get those two because that's recycled information. But additionally, we know the multiplicity, well, we know the crossing and touching behavior of 0 and 1. We figured out the multiplicity and thus the behavior at 0. So the graph crosses at x is equal to 0, and the graph touches at x is equal to 1. So let's go ahead and write down that information down here, because that's going to be helpful. So crosses there, touches here. And the reason why that is helpful is because this tells us that the signs will alternate around anything that crosses, and the signs will repeat around anything that touches. So since 0 crosses, then if there's a negative on one side, then it has to alternate on the other side, because that's what it means to cross. But then with touch, for the right side of 1, that means that the sign will not alternate, which means it will just repeat. So that's why knowing the multiplicity is really helpful, because you can shortcut just like this and not have to do a bunch of tedious computations. So that's why this method is very helpful. So from here, we can denote the intervals above the x-axis and the ones below the x-axis simply by seeing which ones have positive signs and which ones have negative signs. So this first interval on the left here, its interval notation is -infinity to -2. I'll use a comma. And then this is the next section with a plus sign. So that's 0 to 1. And then the final section over here is 1 to infinity. And then below, there's only one spot with a negative sign. So -2 to 0. And we're going to go ahead and put that in answer choice C, because that's the one that has a blank for above and below. Finally, we can use all of this information to construct the graph. Now it seems that the difference between all of these is the location. So we can use process of elimination here. So for example, part A says that the vertical asymptote is on the right-hand side. And in particular, we can count and see that it says that the vertical asymptote is at +2. We found, though, in this problem that the vertical asymptote is -2. So again, this graph says that the vertical asymptote is +2, but we found that the vertical asymptote is -2. So that means this one is out. And also, it might be hard to see, this one also says that the vertical asymptote is in the wrong place. So answer choice B would be out. So both C and D have the vertical asymptotes in the right spot. But what about the horizontal one? This one says the horizontal asymptote is at -1, as opposed to this one, which says that the horizontal asymptote is at +1. So which one is it? We found that it's +1, so it has to be answer choice D. And so that concludes this problem. I did these last two. So I did number 11 here, and number 12 should be fairly similar. I did number 13 as well in example 3. Number 14, I did one very similar in my lecture. I know I did one of these in the workbook session, so I'll do the other one. I did number 18 in the workbook session, if you were here for that, or if you need a refresher on how to do 18, I did that one there. I suppose with the remaining 10 minutes, we can kind of go through these last few. So number 19. Number 19 wants us to determine which one of these is a correct attribute of the graph. It asks about the x-intercept, the y-intercept, and the vertical asymptotes. So hopefully this one shouldn't be too bad to determine, because if we were to figure out the vertical asymptote is, so hopefully you remember, Vertical asymptote is when you set the denominator. Well, to figure out the domain, remember the domain, you set the denominator not equal to 0, and you can figure out x really quickly. And remember, the vertical asymptote just says switch the sign. So we already have that the vertical asymptote is b. If you tried to figure out the x-intercept is -6 in this problem, so that's not correct here. The y-intercept, when you try to figure it out, you'll find it's 6/5, and we figured out the vertical asymptote is -5. You can also look at this problem as well. So if anything, we don't have to worry about oblique asymptotes, really. We can see from this problem that the domain we set the denominator not equal to 0. We can quickly find that x cannot equal -2, which means the vertical asymptote is x is equal to -2. But this problem for part H says that the vertical asymptote is -1, so that can't be right. Additionally, the horizontal asymptote it has to deal with the degree of the numerator and the denominator. The degree of the numerator is 0, and the degree of the denominator is 1. So when the degree of the denominator is larger, this means that the vertical asymptote is y is equal to 0 every time. So I have that in the notes, and I explained that in the lecture as well. G cannot be right because it says that the horizontal asymptote is 2, so that can't be right. However, something to notice, the horizontal asymptote is y is equal to 0, which is a horizontal line on the x-axis. Notice which choice that satisfies, at least initially. The x-axis is its horizontal asymptote. That is correct. This statement is correct. And then it goes on to say the y-axis is not the vertical asymptote. That's correct as well, because the vertical asymptote we found is -2. That is not on the y. See, so vertical is up and down. It's on -2, which is not the y-axis. So really, just by that information alone, we can determine that answer choice D is the correct statement. Okay, so let's keep going. So the interesting thing here is that with this problem, it's not fully factored, which means we might not be able to see the whole picture. So if you might notice, the numerator is a difference of two squares, which means it could be factored. It's x plus 3, x minus 3. And now you might notice there are two factors that can be canceled, the x minus 3's. So we haven't seen this before. But what that means is that what this means is that there will be a hole at x is equal to 3, the 0 that corresponds to that factor. So we haven't really seen that before, but that's what this cancellation implies, which means it is not a vertical asymptote whenever you can cancel out one of them. So I wanted to make sure everyone was aware of that nuance. So I did this one in the lecture as well. Let's go ahead and do this one and we'll call it a day. So here it just gives us some random function and then it says determine the which graph this corresponds to. So if anything, we can go through and try to figure out the domain, which means setting the denominator not equal to 0. But this is a quadratic, which means we need to go ahead and factor it right fast. So then we get that x cannot equal -1 and +5. So already there's one of these that I'm seeing we can cancel out. Because what this also says is that the vertical asymptote is x is equal to -1 and +5. One of these definitely doesn't work. In particular, it's this last one. Because it has asymptotes at -5 and +1. So it has the signs all messed up. So it definitely cannot be this last one. So it's got to be one of the first three. Additionally, we can go ahead and figure out the horizontal asymptote, which means we need to find the degree of the numerator and the denominator. The degree of the numerator is 1, it's just a lone x, and the degree of the denominator is 2 because of the x squared. When the degree of the denominator is larger, the horizontal asymptote is always y is equal to 0. Now we can go ahead and eliminate another one of these. Ideally, this one. And the reason why we can eliminate this one is that it has the horizontal asymptote shifted up. As you can partially see right here. They don't have the dotted lines for you. So it's got to be one of the middle two. And then it's a matter of, is the graph happening above the x-axis or below the x-axis? And to figure that out, we could just simply plug in any value to verify what the outcome is. So I'm going to plug in 10 because for the second graph, it says if you plug in 10, you'll get a negative number. And for the third graph, it says plugging in 10 will give you a positive number. So we get a positive number. So it has to be answer choice with a third graph. So that's all I have for today. Other than that, if you have any questions, shoot me an email and have a good day.